Hi guys, my name is Sanskar Sharma and I will welcome you all in my metrology assignment video. The topic of my assignment video is challenges of accumulation of tolerance in various industries. So first we need to talk about tolerance. What is tolerance? So tolerance can be defined as magnitude of permissible variation of a dimension from the specified value, or we can also define it as a total number of variation permitted in the size of dimension, and it is the algebraic difference between upper and lower acceptable dimensions. So what is the purpose behind tolerance? Let's talk about it. The purpose behind tolerance is to permit dimensional variations in manufacturing of various compounds in various industries. Some accuracy standards used in industries are ANSI and ASME. So as we are talking about tolerance, so it is impossible to make anything of exact size. Therefore, it is essential to allow and definite tolerance or permissible variation on every specified dimension. So as we know that we cannot design anything perfect, there may be a variation in the dimension with the dimension that we are up to. So as we can see in the figure 2.3, where we are making a part to achieve a diameter of 40 mm. This is called the nominal diameter. The shaft will be satisfactory if its diameter lies between 40.05 to 39.95. So the dimensions, that 40.05, that is the upper range of dimension, and the dimension 39.95 is the lower range of dimension. So the difference between the upper and lower limit is called as tolerance. So tolerance in above example is the difference between the upper limit and lower limit, that means 0.10 mm. So tolerance is always a positive number. Accordingly, tolerance on the shaft and holes are decided by the following methods as it is written in this slide. So there are two methods. Let's talk about each one by one. The first one is complete interchangeability and the second one is statistical approach. So in this diagram, as we are seeing, it is the method that is explaining about complete interchangeability. So in complete interchangeability, no risk is taken even for a single non-conforming assembly if the fit between shaft and hole is clearance type. Here tolerance on shaft is equal to tolerance on hole. So we can say that in complete interchangeability process, tolerance on shaft will be equal to tolerance on hole, and it will be equal to half of the maximum clearance minus half of the minimum clearance. As we are watching that here in the diagram, it is clear that this diagram is showing the complete interchangeability process. Now we have to talk about statistical approach. The statistical approach bases the permissible tolerance on the nominal or normal distribution curve. This approach allows wider tolerance and permits cheaper production methods in mass production. Now let's talk about tolerance accumulation or tolerance buildup. So what is tolerance buildup? So if a part comprises of several steps, each step having some tolerance over, so its length, then overall tolerance on complete length will be the sum of tolerances on individual lengths as shown. So in this figure we can clearly see that there are three parts of a compound: part A, part B and part C. So the tolerance of part A is plus A minus B, part B has tolerance of plus C minus D, part C has tolerance of plus C minus F, and the respective lengths are L1, L2 and L3. So the total tolerance is plus A plus C plus E minus B minus A D minus F. So this overall tolerance The sum of tolerances is called as tolerance accumulation. So, what is written here? It is written that because the operator can machine to the upper limit of the shaft, still having the whole tolerance left for machining before the part is rejected. In drilling, the most in drilling dimensions are most likely to deviate in one direction only, that is oversize rather than undersize. Now we can understand the text that I read by the diagram that is shown here. So now we can specify the tolerance in assembly. How to specify the tolerance in assembly? So the type of assembly on fit between the hole making parts will be decided based on the functional requirements. This is the important point, that the type of assembly on fit between the two mating parts will be decided based on the functional requirements. Functional requirements is very necessary point. Now we have to talk about tolerance dimensions. What are tolerance dimensions? So tolerance on a dimension may be either unilateral and bilateral. There are two types of tolerance dimensions. So a tolerance dimension is bilateral if limits are given above and below the nominal size. So if we have given the limits above and below both, then it is bilateral tolerance. For example, here in the figure you can see that it is the required dimension is 40 and the tolerances are plus minus 0.05. So we can say it as a bilateral tolerance. When the limits of the tolerance or dimensions are only above the nominal size, then the tolerances are said to be unilateral. So in the figure there are two figures here. So in the first one or in the second one, both have only one sided tolerance. First one has upper sided, other one has lower sided. So these are unilateral tolerances. And in general life, unilateral tolerances are preferred over bilateral tolerance. This is a very important point, that we prefer generally unilateral tolerances. This method of specifying tolerance results in high tolerances on the overall length. The effect of accumulation of tolerance can be minimized. So how can we minimize the tolerance? This is here we have to talk about how can we minimize the tolerance. So the effect of accumulation of tolerance can be minimized by adopting progressive dimensioning from a common datum. This method of progressive dimensioning has to be established from a particular datum. The overall dimensions are placed outside the smaller dimension. This dimension is showed by the common reference line. So here we made a reference line, and progressive dimensioning process is shown here in this figure. Here we have to measure the dimensions with reference to a single line. That reference line that we have made, so all L1, L2 and L3 are taken from with respect to this reference line. So this is a method that is accumulated to minimize the effect of tolerance. Now what we have to now we have to talk about several methods. Okay, so what the problems that a tolerance can produce in various industrial processes? So we have to talk about that. So the tolerance can introduce unforeseen consequences if you are not careful. So we have to minimize the tolerances. So the room provided by tolerance is absolutely necessary, but if we don't use them properly, so we can easily end up with usual parts. So if we will not minimize the tolerance, then we have to deal with unusable parts. This happens because you have multiple tolerances, and if we add these tolerance, that will result into a big tolerance, so which is called as tolerance stacking. So here we are discussing about one problem that generally we face in tolerance accumulation, that is a compounding problem. So here we take a look at the dimensions of the part shown above. So here we can see the problem. At first glance, we might assert that this tells the manufacturer that the rightmost hole can be between 189.0 to 190.10 from the left edge. What I said that the rightmost hole can be between 189.90 and 190.10 from the left edge. But in reality, this tells that it can be anything from 189.50 to 190.50 mm. That is because each dimension is based on the feature before it, which is flexible by 1/10 of millimeter in either direction. Now, what are the type of tolerances in stack-up analysis? We have to talk about the type of tolerances in stack-up analysis. So, various tolerances stack-up analysis methods are used to calculate optimized tolerance value. Now, we are talking about the methods by which we can calculate the tolerance values. So, first one is worst case analysis. This utilizes simple arithmetic add and subtract operations to calculate optimized tolerances. In this method, all dimensions are assumed at extreme limit. For low production in industries, it is used. So this is an important point. It is used in low production industries. What we have to do in this. Let's talk about it. We will calculate overall maximum and minimal tolerances stacked disk height using worst case tolerance stack up analysis method. So let's talk about various steps one by one. Step 1, calculate total nominal thickness. It is calculated by adding the total nominal thickness that we have taken in previous figure in the dimensions. So we are adding up the same. You can refer that. So here we added 15 plus 10 plus 15 plus 12 plus 15, so we got 67 mm. This is the total nominal thickness. In the second step, we have to calculate total tolerance. Next step is the addition of total upper and lower tolerance. So we have to add them separately. So in total upper tolerance we got 1.5 mm and lower tolerance we got minus 1.5 mm. Now we have to calculate total tolerance. So total upper tolerance is plus 1.5 and lower tolerance is minus 1.5. So maximum height is equal to upper limit of the tolerance. This is the important point. So now we have to calculate about nominal dimension tolerance. Nominal dimension plus tolerance gives us the maximum height. Maximum height is also known as upper limit. So how we calculate maximum height? It is the nominal dimension that we have calculated in step 1 plus tolerance, total tolerance, or upper tolerance. Upper tolerance we calculated in step 2. Okay, so we got 68.5. Similarly, we calculate minimum height. It is lower limit plus nominal dimension, same as maximum height. Here we got 65.5 mm. Okay, now what are the advantages of this method? Worst case tolerance stack up analysis ensures 100% part assembly on production floor. So this gives 100% part assembly on production floor. What are the disadvantages of this? Worst case tolerance analysis requires very tight individual component tolerances. It increases overall manufacture and inspection cost. So this is not acceptable. because it increases the cost, so it is very costly. Worst case tolerance analysis example. Here is an example of worst case tolerance. We can see multiple disks and various tolerances. So let's consider an example of 5 different size disks with different tolerances stacked on one another. This is an example of worst case tolerance. So what is the conclusion with above example? What conclusion we got? So in the above example, the total stacked disk or the thickness will vary from 65.5 mm to 68.5 mm as we calculate about maximum height to minimum height. The range of maximum height to minimum height is 65.5 mm to 68.5 mm. Let's move on to another method, that is statistical tolerance. Statistical tolerance analysis does not forces on the extreme dimension limits. As we see that we have seen it previously that worst case tolerance forces the extreme dimension limits, but it does not forces the extreme dimension limits because variation in manufacturing part is non-linear. As we can see in the graph that the variation is not linear, it is a curve. In the graph we can easily see that. So what are the advantages of statistical tolerance? Statistical tolerance stack up analysis helps in increasing component tolerance limits. In the worst case, part tolerance becomes very tight that increases the part cost. These are the advantages of statistical tolerance. So thank you guys. I hope you like this video, and I hope you like my research work that I made on this tolerance accumulation video. So thank you and have a nice day.